Good morning to everyone. My subject for presentation, my paper number 11426 is time-dependent material response of transverse impact on model beams. In this case, there are two types of experiments were carried on. One is dynamic photoelasticity using material urethane rubber PSM4, and a second set of experiment having electrical resistant strain gauges, contact force transducer, where the beam is of different material. It may be PMMA, aluminum, or layered composites having PMMA, aluminum in between, and PMMA. The model beam is having equal overhang and simply supported. The striker is a free fall through a guide pipe is going to hit either at the central or at the quarter span impact point. In this experiment, the few things are kept constant, that is beam striker weight ratio 2.675, height of the fall of the striker, that is 176.4 millimeter, and dimensions of the beam. In the case of dynamic photoelasticity, a framing camera named Fastax was used, operating 12,000 frames per second. The arrangement for polariscope in this study is kept light field arrangement, because when we are going to record through this camera, the movement of the striker and the location of the datum will help us to find out the contact velocity of the striker through the experiment, and the datum will help us to find out the deflection of the beam at different frame while recording. The arrangement here, the two sun gun placed side by side with uniform illumination, diffuser plate, and the lens is having a interference filter, green filter, having band pass of 100 angstrom. Below there is a typically large photograph from the 16 millimeter film is been shown here. The arrangement for the dynamic photoelasticity experimental setup is shown in this photograph. The main camera, which is in the number 5 position, and the optical arrangement, which is kept in the frame, and the guide pipe and the electromagnet. This is supported over a platform, namely aluminum, so that it doesn't have the contact with the electricity, non-contacting material. The two sun gun, as you see it here, the control will be discussed later on through the goose control unit. The different strikers construction are kept as it is showing in the figure, namely 1, 2, 3, and 4 and 5, they are used. Second set of experiment. In this case, the mild steel, which is cut inside, is used for making the beam striker. The ratio is constant. The tip of the striker is made with the araldite so that the contacting material urethane is not highly dissimilar with the contacting material. The photograph is identified here to show the shape of the different strikers in actual black and white photograph. The three different striker for dynamic photoelasticity, namely 90 millimeter beam, 10.52 gram. For 120 millimeter beam, striker is 14.02, and for 150 millimeter beam, striker was 17.53. The arrangement for support of the beam, which is a variable due to the two screws provided with the wedge-shaped support, 1 and 2. It may be 90, 120, and 150 millimeter. The arrangement for the dynamic photoelasticity with camera is critically, it is been observed with a method of synchronization. This is striker in the schematic diagram. The model beam is a camera and the light source. Here, the relay is placed where in the normal position or in the record position, the time marker and the goose control unit, which is activated through the press button. There are 7 steps through which the synchronization was done. Number 1, the time of fall of the striker was measured by a starting timer circuit operating the electrical switch and stopping a metal foil short circuiting. This time measurement is important to have a setting in the control, which is a goose control unit, and event marker. Second, depending on the framing speed desired and the total length of the film used, the voltage control, the camera time of the goose control unit were then set. Third, the relay in the figure 4 was in the normal position by which the electromagnet was energized. Next, fourth step, all lab light were switched off and the sun gun toggle switch was on. Fifth step, the press button switch in the time marker are pressed. The micro switch operated in the relay will be in the record position, and in that way, the relay in the D energizes the electromagnet, simultaneously switching the goose control unit, and goose control unit started motors of the framing camera. By the time the striker hit the beam model, the desired camera speed was achieved. The camera was automatically switched off by the camera time control provided in the goose control unit, and therefore the recording was completed. And last, the time marker, press button, and the sun gun toggle switch were switched off. By this way, we get the recording for 3 different beam, namely 90 is a case of C, and B for 120, and A for 150 millimeter isochromatic fringe pattern with the light field arrangement. Enlarged photograph for the 3 cases are also shown in this case in the different in time. It is a 4936 microsecond situation. In the C case 90 millimeter, it is 1897 microsecond, and 120 millimeter selected frame is 2523 microsecond. The fourth one is typically taken a enlargement on the photographic paper with a millimeter grating. The millimeter grating is clearly seen on this, and detail will be used for recording the fringe time frame wise and to plot the boundary stress distribution. This is a non-central case where A for 90 millimeter, B for 120 millimeter, and C for 150 millimeter. This details is giving a typically a different situation than the central one, which will be discussed. This is enlargement for 90 millimeter. The enlargement for this is time for 1352 microsecond, and 120 millimeter is a 4238 microsecond time frame, and C 150 millimeter beam for 3361 microsecond. Now, using the isochromatic fringes, we can find out the details of the trace wave propagation. We can also measure the contact velocity, the boundary stress, also deflection, which is not reported here for central and non-central impact cases. Utilizing the results was observed that 120 millimeter beam considered to be very important for the designer's point of view. So we find out the second set of experiment. The grating that is being used millimeter over the photographic paper was clearly showing the location of the different values of the fringe at the boundary stresses, and distribution of the stress can be plotted very clearly. That is known as free boundary stresses, both for central and quarter span impact position. This is the result of a particular time 757 microsecond phenomenon. Here, this is the plot for top boundary, this is a plot for the lower boundary, and incidentally, there is a rise in the tensile stress on the top at the bottom boundary. This free boundary stress distribution for 120 and central impact is symmetrical. That's the reason it is plotted half of the beam, but on the case of a non-central case, the distribution is not symmetrical. That's why it's plotted for the entire boundary of the beam. And this is chain dot line representing the top boundary. The solid line represents the lower bottom boundary. This is the sequence for 848 microsecond phenomenon, and the lower one is 1272 microsecond phenomenon. The fringe pattern, which is a order, can be seen very clearly with a strip of millimeter grating. And the second experiment, which is performed with the help of the storage oscilloscope, which is showing in the here, and this is power supply. The guide pipe, which is carrying the electromagnet and the release of the striker, will pass through a light path. This is a DC volt light path, and the photo transistor, which will help to record the movement of the striker and the time taken by the striker to hit the model beam. This will facilitate to find out the contact velocity experimentally. And the contact force transducer is fabricated by me, and the signal is fed to a charge amplifier, which is connected to oscilloscope to record the force, and the strain gauge, which is marked at the bottom of the beam or on the top of the beam, is recorded in the second channel. There are two channels in the recording system here, and the storage oscilloscope helps us to record, and we can find out the result on a millimeter on a Polaroid camera. So this situation for the dynamic photoelasticity using urethane rubber beam model at the central and quarter span impact point, the overhang is varying from 0.24 to 0.322, and impact with the constant velocity ranging from different 1.12, and the value is less than 2 meters per second in any case. The span depth ratio varying from 3.711 and 6.186. The beam striker weight ratio is always constant. The significant case, the behavior for due to the overhang, the generation of the semi-infinite plate behavior can be seen the enlarged photograph here. You can see this point load is just like impact coming, spherical pressure valve will be propagating. This situation is called semi-infinite plate behavior. And other cases when the compression pulse is going to hit and we get the reflection from the bottom boundary producing the tension pulse, which is clearly seen in the diagram, which is the isochromatic fringe pattern. The movement of this stress waves, when it is stabilizing in between, we get a typically the zero order formation on the top and bottom, and this zero order, which is coming, if we draw the bending moment diagram for a elastically supported beam, we find the sagging bending moment and hogging bending moment near the support. So this is typically is a behavior, we call it as a elastically supported beam behavior. But in the case of the non-central impact, there is, because of the proximity of the support and the impacted point, there is a compression, direct compression. So we define as a simple compression behavior in the case of non-central impact. The second set of experiment with the material of the beam, perspex and perspex aluminum perspex. Perspex is PMMA and aluminum. We get the results is plotted along with the Hertz constant with the striker tip and the beam material. So this table consists of the peak tensile strain for the three beam and the striker beam weight ratio and the Hertz constant and normalized one as well as the real one is been showing in the diagram. The another table which is marked by different striker on a perspex material of the beam, they're having 14.02 gram, 29.52 gram, and 41.5 gram strikers. The Hertz constant between araldite and perspex corresponding to the striker weight 14.02 is calculated, and the table 2 is giving the striker weight, Hertz constant, Hertz weight, and the beam weight, and the peak tensile recorded in this diagram. These two tables will help us to produce a normalized with help of the striker weight and the beam striker weight ratio is calculated. The values of normalized Hertz constant, striker beam weight ratio, and peak tensile strain for perspex beam is plotted in a nomogram figure 13. For the 14.02 gram striker, peak tensile strain and normalized Hertz constant, estimated a reciprocal relation between normalized Hertz constant and peak strain, and this diagram is plotted in figure 13. This is showing here. This helps us to get the nomogram, which is between the normalized Hertz constant, striker beam weight ratio, and peak tensile strain. It will, if the material other than these three, we can interpolate the Hertz constant, we can interpolate the beam striker weight ratio, and we can predict the strain in the new material. The second nomogram, which is having the normalized the Hertz constant, striker beam weight ratio, and peak tensile strain for perspex beam under central impact loading with different strikers. So if the striker is changed and the normalized Hertz constant, we can find it out with the help of beam striker weight ratio, the strain or the peak strain developed in the material for similar type of impact loading. This is a typically oscilloscope trace with the strain boundaries for the perspex beam under central impact loading by 41.5 gram striker. This gives you the two gauges on gauge 1 and gauge 2 location. Here in the horizontal sheet, the time is one is a 200 microsecond. In the ordinate, it is giving the voltage, and in turn it is calibrated with a microstrain. So we can find out the peak strain from the diagram. The horizontal sweep, which was discussed in the second set of experiment, gives you the time measured by the striker to hit the beams. If the time is taken t, then we can find out from the guide pipe location, this is the bulb, light source, this is the photoresistor, and the travel time of the striker to hit the beam. If the d is the distance, then we can calculate experimentally the contact velocity d divided by t. The different type of composite plot of the strain histories at the central location and quarter span location and the quarter span location from the top and bottom fiber is showing here for the sake of understanding the different behavior as well as the left quarter span. So from this diagram, we can get not only the peak and the behavior of different type of situation or the different material in one composite plot. Similarly, this is also a composite plot for the central impact, how different material is going to behave under central impact condition. The other two, left quarter and right quarter, one is going to give the idea, the location of this strain on the beam on top and bottom, as well as left and right side of the strain gauges. So in this, we can find out an important incidence, which is the presence of the small amplitude precursor in strain histories. The number of strain histories with the strain gauges on the top and bottom boundaries of the beam, with the exception of the urethane rubber beam that is presented in figure 14 and 15. You can see clearly this is a compression strain, and there is a value of the small amplitude precursor even in strain gauges. And in the quarter span point location, this is more prominent. In the case of urethane rubber beam, the free boundary stresses, which is showing in the figure 10 and 9, also indicates the rise in tensile stress on the top as well as on the bottom boundary. So this showing as a small amplitude precursor, which is such that the material which is having a fringe pattern is going to give us a semi-infinite plate behavior. There is a load on a semi-infinite plate. We get a compression bulb. As it is going to reach the boundary at the bottom, it is a reflection will produce as a tensile pulse, and that is going to give us a precursor in the beam. The peak value of the stress or strain employed in the preparing the beam should be capable of withstanding significant amount of tensile stress, both for the top about fibers also, and that is in the vicinity of the support location. And I give the acknowledgement for my research to the Terminal Ballistic Research Laboratory, Chandigarh, in India, for providing all necessary facilities. Thank you all.